Have you ever looked at a system, a process, or an organization that's clearly on the wrong track and wondered, why don't they just fix it? Today, we're going to explore that very puzzle, why some complex systems become truly impossible to reverse.
Most of us operate on a pretty simple assumption. If a system is producing bad outcomes, we can change it. We think we can just unwind a bad decision or go back to how things were before. But when we actually look at how complex systems behave, we see something totally different. They have a tendency to lock in, to become irreversible.
And that leads to the central question of this whole explainer. If a system is so obviously headed in the wrong direction, why can't we just go back? What is it that makes reversing course so hard and sometimes completely impossible? To get to the answer, we have to dig into the mechanisms that are working under the surface.
First, we need to tackle a core belief that trips us up. This idea that system change is a two-way street. The reality is, it's often a one-way mechanism.
The journey toward this point of no return, well, it starts small. It begins with little, almost random events that, over time, end up becoming permanent parts of the system's DNA.
The main idea here is something called path dependence, and it's actually a pretty simple concept, but its effects are huge. It just means that history matters. The choices a system can make in the future are hemmed in by the path it's already taken. Every decision, even a tiny one, starts to carve a channel that makes it easier for all future decisions to flow in that same direction.
Okay, so let's use a really simple, abstract example to see exactly how this works in practice. Imagine an organization that needs a standard way for all its teams to share data. We'll just call this the standard protocol. At the very beginning, they've got tons of options. Now, one day, a single team is on a really tight deadline. They pick something we'll call Protocol A. Now, it's not necessarily the best option for the long haul, but hey, it's there, it works, and it solves their problem right now. This wasn't some grand strategic move. It was a small, perfectly rational choice made in the moment. You could call it an accident of history. So what happens when the next team needs to choose a protocol? Well, they look around, and they see Protocol A is already being used. It's just easier to adopt it than to start from scratch and evaluate every other possible option. It quickly becomes the path of least resistance. It becomes the default.
And here's a little micro example of that. A new team comes on board, and they make the very logical choice to use Protocol A because it'll help them integrate faster. Now, from the outside, the system looks like it's working perfectly. Efficiency is up, standards are being followed. But what's happening quietly under the surface is that the dependence on this one single protocol is getting deeper and deeper, creating a hidden vulnerability.
But it's not just that the system sticks to the path. This is the critical escalation. The path itself starts to pull everything towards it, almost like it's creating its own gravity.
This happens because of a reinforcing feedback loop. It's pretty straightforward. The more people who adopt the path, the more supporting infrastructure gets built around it. That infrastructure then makes being on the path even more valuable, which, you guessed it, encourages even more people to adopt it. It's a cycle that feeds itself.
So let's go back to our example. Protocol A isn't just a choice anymore. It's an entire ecosystem. The organization is now invested in specialized tools, they've got training programs, they might even have dedicated support staff, all built specifically for Protocol A.
And this is where the trap becomes obvious. A brand new, objectively better protocol comes along. We'll call it Protocol B. But switching to it would mean throwing out that entire ecosystem. You'd have to retrain everyone, buy new tools, rewrite all the procedures. So the cost-benefit analysis is run, and the conclusion is clear. The most rational decision is to stick with the inferior Protocol A. The system is doing its job correctly. It's optimizing for cost, and in doing so, it locks itself even deeper onto a suboptimal path.
So as this one path gets stronger and stronger, something else is happening in the background. All those other possible paths, they start to weaken, and eventually they just disappear. Think about the system at the very beginning. It's flexible. It's standing at a crossroads with a whole bunch of potential futures branching out in front of it. Lots of different paths seem viable, and the space of what's possible is wide open. But after path dependence and those feedback loops have done their work, the landscape looks totally different. The chosen path is now a deep, well-worn highway. All those other potential paths have just withered away from lack of use. They aren't real options anymore. The future has basically collapsed from many possibilities down to just one.
We call this state lock-in. And what's important to understand about lock-in is that it has nothing to do with whether the chosen path is the best one. It's a state that's defined purely by transition costs. The system is trapped not because the current way is so great, but because the cost of leaving it has become way too high.
And that brings us to the deepest and maybe the most counterintuitive mechanism of all. The system doesn't just get stuck on a path. The system itself fundamentally changes into a new, stable state that actively fights against being changed.
The best way to picture this is with a metaphor. At first, the system is like a ball sitting on a flat, level surface. You can push it in any direction with just a little bit of effort. But after lock-in, that system is like a ball that has rolled to the bottom of a deep well. It's found a new, stable equilibrium.
And here is the absolute key insight. Getting that ball out of the well takes a massive amount of energy, way more than the gentle nudges that caused it to roll in there in the first place. Reversing the system is no longer a symmetrical action. You're not just making a different choice. You are trying to overcome the immense gravitational pull of this new, stable state.
At this point, the system's own structure is now built to maintain this state. People's careers, departmental budgets, performance reviews, they all depend on the existing way of doing things. The system isn't just passively sitting on a path anymore. It is actively preserving that path for its own survival.
Okay, so when we put all these pieces together, path dependence, those feedback loops, lock-in, and these stable states, we can finally see the underlying logic of why systems become irreversible.
And here's the kicker. The irreversible trap that we've been describing, it isn't the result of the system breaking down. It's actually an emergent property that comes from the system working exactly as it's supposed to. It's the logical, cumulative result of thousands of small, rational, local decisions all made over a long period of time.
Which leaves us with a really provocative final thought. Systems don't fail because somebody made a big mistake or broke the rules. They very often fail because everyone followed the rules perfectly and the system diligently followed its own internal logic, right to a conclusion from which there is simply no going back.